7:30. Let's get started today. So you have this project one due tonight, right? So all you are done. Okay, good. That's good. Yeah. So remember, this was the easiest 100 points probably in the whole semester. This is main target was to get yourself acquainted with this model sim environment, little bit on the Verilog language, little bit on the writing a good report and stuff like that. So the next project 2 is going to be really, really difficult. So please start early. There is no time for partying and everything right now. Okay. Project 1, you are done. Fantastic. Easiest project. Your environment is set up. You're ready to go for take up the complex project like project 2. So start early on that. And as I established the study groups in the Canvas, you basically take advantage of that, study together in the group, clear up each other's doubts, etc. You can definitely discuss your problem, like the project problems and stuff like that. Just do not share code with each other. Do not copy paste from each other. That's the only criteria. Otherwise, you guys can solve each other problem and pick out strategy, discuss strategies, how to solve problem, etc. And also you guys can share at least the test benches, test code that you will be developing. You can share among with each other so that your writing test code would be less burden. Main idea is to make sure you understand how to implement a processor from the behavior, how to describe a processor from behavior perspective, so that you know what goes on inside a processor. Like if you want to think processor as a human brain or something like that, what goes on inside the processor? That's what is targeted for this project too. It will give you pretty much good insight of how a processor works, what goes on inside that. So basically, that's about the project too. Make sure you start early. Any questions on today's topic or anything else on the previous topics, etc.?
That's a new question in the Q&A. I don't know if you're going to get to those, but I thought if
Q&A? Okay, yeah, I haven't looked. Today morning I didn't find any, but let me see.
I just submitted it like an hour ago. Or
okay. Let me take a look. Quizzes. Discussion. Okay, module 3. Yeah, that's an interesting question. Let me share that. So the question is, couldn't you eliminate the rest condition by doing that? Make one wire length mirror its mirror wire. Okay. So you're depending on the speed, on the delay of that conducting material. That's what your thinking is. That's a good thinking. In fact, in the asynchronous circuit, some of the rest problem are solved with introducing delay elements between them. Yes, theoretically it is possible to do it, make one gate is winner of the other. But point is that why should we do that unless it is absolutely needed? It is all about your return on investment of your doing. Remember, more longer wire you put on the chips, it is basically harder to route the chips, because that chip has like billions of wire and interconnects going around each other in a processor. So making long wires longer is sometimes really problematic. Um, Sometimes we need to do that for solve other problems like electromigration problems and other, but not necessarily, at least on the digital perspective, synchronous circuit perspective, we don't go for that. We basically want to have more control, deterministic control over what goes as output. That's the reason. So friend, is that explains?
Yeah, totally makes sense. Thank you.
Okay, Catherine asked, could you please explain about SR latch, SBar RBar, and D latch again, and what the outputs for each of the input? Okay, yeah, sure. And that also, yeah, we can do a experiment on the Verilog side on that part. Yeah, but if you have any specific, Catherine, can you tell me anything specific about that? What's bothering you most?
Nothing like specific. It's just that the whole like concept, I think like if I could like hear you explain it like real time, like I would like really understand it more.
Okay, sure, I'll try that. So let's try it. How should we do that? Okay, stop share and share. Okay, so let's start with the SBar RBar latch, right? So this one is more like uh, like a most basic storage element we can have. So we are trying to make a feedback circuit which basically outputs drives each other. An assumption is that we have an output and its complementary output. So both are the outputs in this case. We can use it or not use it, that's a different story. And why it is named SBar. So don't get confused that this bar has to do anything with the like inversion of logic or something. It is just a mark. It is just a mark saying that this action, set action, would be performed when SBar equal to 0. This is just a name, but it's indicate that this will perform, like its function would be set function will perform according to that. And similarly for the reset, it is just a naming RBar, nothing else, nothing to do with logic. Somewhat it is representing that its reset will be performed, action would be on RBar equals 0. So what happens here, like if we have like a, like a 0 here and 1 here, right? So at that point, this output will be definitely 1 because that's a deterministic logic on one input for the NAND gate. And no matter what this guy is, like we don't know what that logic is, but still it will make this output Q to 1. And then 1 and 1, this one will come here and make 1, 1 as a 0 of the output. So with the S bar and R bar, we have 0 and 1 that will make, like, no matter what the output was at the previous point of time, we don't know, right? From there, it will make, so that's what the QT and T plus one tells you, that Qt is the what is my current state or current value of the logic when this 0 and 1 was supplied or applied to that. So no matter what the Qt is, the Qt plus the next value of the output would become 1. Thus your Q bar T plus 1 will become 0. Now from here, if you change the value to, let's say hold condition, right? 1, 1. So what will happen if it is 1, 1? Then this logic was 0 from previous, 1 and 0, still 1. It will have the 1 as a new logic, and 1, 1 will still have 0 as a new logic. So it is kind of as if my Qt was 1 and I'm holding that value. And this guy is 0. Now you make this guy 0 and this guy 1. Sorry, the other way. Make this guy 1 and this guy 0. So this will change the Qt bar as to 1. So that means this one will become 1 and this one becomes 0. So from here, if I have 1 at the S bar terminal, R bar as 0, then Qt, if the current value, no matter what, basically, let's say in this case it was like what, 1, then it will turn to 0. Right? And this guy will be 1. And then you basically change it to 1, 1. That's a hold condition. So previous value was 1, it will be held, sorry, previous value was 0 in this, from this point, it will be held as 0 and 0, right? 0 and 1. And from there, you can actually start changing the logic value like this, and we'll see that ultimately what you can discover is this part, right? No matter what the Qt value is, if you set the S bar terminal to 0 and R bar terminal to 1, the next logic value would become 1 on the Q terminal. And no matter what the previous output of that specific circuit, if you set S bar to 1 and R bar to 0, it will basically change the output Q to 0 after applying the logic, and that's a reset condition. And if you keep 1, 1 at that S bar R bar, it becomes like your if Qt or the previous, that current logic at the Q terminal is 0, it will hold that logic value, and if it is 1, it will hold that logic value. It will become 1, will stay at 1. And 0, 0 is undefined in the sense that you can see that, let me just reset it. Let's say somewhat, let's say somewhat this output was 1 and 1, 1 and 0, right? And you apply 0, 0. So by logic, that means it will stay at 1 and this will become 1, right? 0 is the controlling value of the NAND gate, and no matter what the other input is, output will become 1. That's not a problem. Now from here, you want to, let's say, go to a hold condition, 1, 1. Okay. Now, what will happen, either this one will act to this logic and then turn it to 0, okay? And that 0 will make this guy 1, or if this one act faster on this guy, right? This guy will become 0 and this guy will become 1. So we don't know who actually wins the race between these two signals, which acts upon this signal or that signal. So basically, we don't know. Cannot predict deterministically what's the value is going to be if we make it, let's say, a hold configuration after 0, 0 is applied. So that's why it is an undefined condition. So far, so good. Okay. Now, with that, what we can do, we can actually do this experiment on the model scene. Let me just bring up my model scene. So who are joining late, actually, please make sure you join like 5 minutes early. I start this meeting 15 minutes before start time. Otherwise, like this time is, I'm turning on the waiting room, always keeping that on. And if I am discussing something, I probably won't even see that you guys are waiting in the waiting room. So to make sure you can attend timely fashion, make sure you are actually early in the meeting. All right, so let's say this is my little bit of example I have written. Okay, let's talk about this SBar RBar latch, right? So what I did here, I have exactly the same one as I like drawn here. With the addition of preset and reset. Now, what is that preset and reset? Is basically it has this 3 terminal and it has another terminal called N preset and reset. So basically, if I make supply a 0 here, that means it will force, no matter what the Q and Q bar, etc., etc., it will force this logic to become 1, and in turn this logic to become 0. But we need to make sure this guy is 1. And now if I actually apply 1 here and 0 here, then it will basically become reset. So this guy will become 1 and this in turn will become 0. So we can deterministically place this circuit to a known output logic condition before if we can start operating on this specific element. So this is called a preset and reset. And in normal operation, we keep it 1-1. So that is a normal operation. Then whole circuit actually will behave like a SBar RBar latch that we described just here. So that's what this module is. Very simple, using 2 NAND, 3 input NAND, and it's feeding back each other, and then it has a preset and reset configuration. And as a test bench, I have this this thing like driver for the SBar RBar and preset reset. So basically, we have this driver for each of them, the registers, SBar RBar, etc. And they are connected, instantiated, and get connected into that instantiation of the SBar RBar latch. And we are supplying these different conditions, right? Set, hold, reset, hold, etc. Where we are keeping the preset and reset to 1, means we are not even presetting or resetting that circuit up front. We are just like putting that whole circuit as a normal under normal condition. So we compile it, we load this SBar RBar latch TB. So I highly encourage you, since you are learning this Verilog and you have this tool in your hand, you can actually do all these small experiment yourself to learn more onto these behaviors. Okay. So okay, what shall we do here? What it is doing? Apparently, it is doing a lot of things. Okay. This is the waveform deck. Let me add SBar, RBar. Okay, why don't I just add all of them? Okay. All right, it is added. And also let's add this on our data flow. So this one, see, like 2 NAND, it has this feedback with each other. It is not nice as this picture, but it is equivalent to that one. Tool automatically drawing it, that's okay. And we have this logic value we can trace through it. And then we can simulate that. And let's see what is happening. Where is that? Okay. All right. Okay, let's look at this one, right? At the very beginning, shall we just rearrange? Okay, let me put the preset and reset over at the top. It doesn't have a function nonetheless. And reset, okay, SBar, RBar, QQ bar. Okay, so at this point, your SBar, RBar is 1-1. But see, the output is all unknown because at that point, we really don't know what the output is. So it is unknown at that point. And that's why this preset and reset is needed in the real digital circuit to make it start from a known state. To make it start from a known state. That's what we are discussing in this sequential element lecture as a initial condition, or G0. That function value, that initial value, that's what we set with the reset and preset. And that's what happens. Like, I don't know whether you have seen the old computers. It has used to have a reset button. Nowadays, it is all about the software resetting. When you do reboot or control alt del everything, like and restart, it basically a soft reset. And what happens at the hardware point of view, a reset signal goes really into all the individual logic gates and flip-flops and this sequential element like this preset reset, and that signal flows into these components and get them into the known initial state condition. So that's really the that reset button is in the old computer system, and now it is soft reset basically. Anyway, now we basically see at this point, we make the S bar 0 and R bar at 1. That makes the Q value goes 1, right? Just like this, 0, 1, Q value to go 1. Now this becomes my current value. And in the next operation, I make the S bar to 1. That's a hold condition. So S bar 1, Q 1, so it will stay at 1. That's what is happening. Q is staying at 1, Q bar is staying at 0. And then this Q is 1 is my current state. And then we change the S bar is keeping the S bar to 1, but R bar to 0. That makes the next output Qt plus 1 as 0. That's the reset condition. And then we keep it at hold, and that hold is done. So that's the behavior we are observing on the simulation environment, and we can definitely look at these logic changes in the data flow diagram on the model sim to convince ourselves that's the way it operates. I would like you to play with this, especially with this undefined condition, and observe what happens if you actually place an undefined condition into the simulator. Okay. Question so far? All right. Now let's move on to the next one. Next one is the latch with a control. Latch with a control. So what is happening that we have these this undefined condition, right? So, and people didn't like that undefined condition to deal with, because that's a dangerous to the overall system, that if some element inside goes into the undefined state, we don't know the behavior of the entire machine. Okay, so entire machine's operation can be jeopardized with that. So we basically go and have a control C, and see here we basically took the bar, like it becomes a S and R. So that means like it kind of indicates that my set operation will be on 1 and reset operation will be on R equal to 1 and S equal to 0. And why? Because there we introduce another set of NAND gate, and that controls the flow of this S and R into the inner S bar R bar latch. So this inner part is really the S bar R bar latch with some control logic at the outside, where C is that control is controlling the flow of the information from S and R into the S bar R bar latch. And then what is happening here, this specific circuit still has an undefined condition. That is, if C is 1 and S and R are 1, then of course the inner S bar R bar latch will be having a 0, 0, which is an undefined condition for the inner S bar R bar latch. Okay, so we still have that. But from this point, we can eliminate that with a little observation, that if the C is 1, okay, and S and R are zeros, they are hold condition, right? This is hold condition, these two lines. And if C is 0, that is also hold condition. Just convince yourself to basically put the logic in and see what is going on. But if C is 0, that is also a hold condition. If only C is 1, then this set or reset actually takes effect. Now in this circuit, we have two hold conditions, right? If either C is 0 or C is 1 and S and R are both zeros. So with that observation, what we wanted to do is simply eliminate possibilities of these two entry or three entries from the table, okay? Why? Because we see the 0, 0 is hold, and if it is 1, then S and R has an inverse condition of doing it, setting it to 1 or 0, right? Either it is 1, 0 or 0, 1. That is allowed condition. With that observation, we derived the D-latch. Basically, we made S and R invert to each other, and that way we eliminate the undefined condition from the whole circuit. Okay, undefined condition from the whole circuit. And D-latch is suitable for making a big digital systems. Question? Okay, so let's observe these like D-latch and let's see how we can derive things from there. So we already wrote a SBar RBar latch. Now we'll use it just like these this thing. No, this is D-latch. Here, SR latch with control. Okay, so there you see I used a couple of NAND gates. These two NAND gates were introduced and instantiation of the inner SBar RBar latch. That's what happens here. Two NAND controlling the S and R, that information flow into the SBar RBar latch, and SBar RBar latch is instantiated with connecting output to the QQ bar itself. We are picking up that output and input as my internal SBar and RBar, which is these wires. Okay, SBar and RBar. So with that, we basically have one more test bench, SR latch DB. And here we'll see that we can observe a couple of things, like it is the hold with a C equals 1, okay, because S and R are both 0. This is set with C equal to 0. Set with C equal to 1 is basically set, and set with C equal to 0 is practically hold. Even if we are trying to set, since C is 0, it will be on hold basically, and that's what also demonstrated at the other part, the reset part. So let's try to load that. Is our SR latch TV. SR latch TV. Okay. Okay, this, and I'm keeping the preset reset to 1. So let's not even observe them. And QQ bar, let's add it to the wave. I can here, and also let's see if I as a latch. Let's add to the data flow. So here it try to flatten it out, this two NAND gate, and this is the inner SBar RBar latch. I think I can unfold these. Let's see. Oh, sorry, I need to fold. Okay, so this is really the one, right? Two NAND with the R and S with the control going to them, and they are fed into the SBar RBar latch, basically. Forget about preset reset right now. And QQ bar is observed in the test bench. So that's what happened. And then we can simulate. And let's see. So SR 00 hold condition with C is hold condition, but initially since we didn't preset or reset, it becomes like unknown. And then we try the hold at this point, try the hold 00, but C is 1, but still it is a hold condition. It is a previous unknown logic will be held. And then at this cycle, see C is 0 and S is set to 1. So since C is 0, we still don't reflect that, that control over the SBar RBar latch. That's why your output is still unknown. Only if we make the C is 1, then that control gets propagated into the internal SBar RBar latch here, right? This latch, it will propagate to that, and that make the Q and Q bar state, like Q to 1 and Q bar to 0. And then we basically at this point, C is 0, we are making it 0 and 1, but it is not resetting because C is 0 is a hold condition. So it is holding on to the previous logic of the circuit. And then as soon as we are making this guy to 1, C is 1, then your output is becoming 0. We are resetting the operation we are trying to make. That's only happen when C equal to 1. Question?
So anytime the clock is at 1, then it resets?
So anytime clock or C is 1, let's not call it a clock. It will become a clock concept, but right now it is a control. This control is as long as this is 1, then only you can control the inner SBar RBar latch. So even if we set the S and R to the reset condition, but since the control is 0, we cannot affect the inner SBar RBar latch, and that's why at this point is Q is not changed. Q is basically unchanged from the previous state. As soon as with the same configuration, as soon as we make the control 1, we are kind of open up the control to the SBar RBar latch for the propagation. So that control propagates to the SBar RBar latch at that point, and then it affects the Q. Question? All right, now from here, let's see the D latch. Let's see the D latch. So what did we do? D latch is nothing but basically we are tying up S and R as an inversion, right? So what I did in the implementation side, so we, oh no, that's test bench. SBar RBar. Okay, let's open up this. So now we basically have an incoming D, so that is this one, and get it inverted through the inversion, not get instantiation of inf1, and then we are feeding this D and D bar in place of S and R of the SR latch. See the SR latch, this guy. So Q bar connected, C is connected directly. Now in place of S, I'm connecting the D, input D, and then in place of R, I'm connecting the D bar. So that's what happening. D and D bar is connected to the SR latch side. And yeah, and then preset reset are there. That's okay. So with that, and I have this test bench for D latch, which is instantiating a D latch, and then basically it is showing you the hold and then Q equal to 1 when we basically D is 1. So it basically Q follows D as long as C is 1. Okay, as long as C is 1. That's what we'll see here. So we can just make it a little bit interesting. Another C is, let's take it out. And D is 1, repeat 0. At this point, we expect this still to be 1, held at 1. And we'll see. Let's see how the simulator works with the 0 delay. And this one, 1, repeat 0, D equal to 1, repeat 1. And we expect Q to be, oh, that case is already there. Okay, let's insert that. Compile. Okay, then pick up latch TV. Okay. Let's see. Let's DCQB. Let's have it to the web. And let's add these in the data flow. Take care of this. Okay, it's kind of unfolding everything. Let's fold. SBar RBar latch. And then fold. Okay, delatch, unfold. Okay, delatch is that we are seeing that inverter going, then we are connecting to the NAND of the delatch there. Fold. Oh, why don't we fold? Oh, here. So SR latch we instantiate and the inverter is added to that. That's what our configuration is according to this case. So inner part is really your delatch, sorry, SR latch with control, and then outer part is your inverted D going to the S and R into that circuit. So we simulate and observe. All right, so here's what is happening here is D's, okay, let me throw the C2 up, okay. C is 0, D is 0, so 0, C 0 means hold condition, and since we did not set this element to any preset or pre-configured value, logic value, it is still unknown. Even if we change the D, it does not affect anything on the Q, still is unknown. As soon as we make the C1, then Q follows the C, follows the D, okay? And then at this point, we have C0 and D0. So Q did not follow D. It basically held on to the previous operation value, which is still 1. But as soon as we are making C up, then it is affecting the Q value, and Q value at that point is going down. And then then the next is hold condition. So that's the delatch operation. Now with the delatch, we'll be moving on to the D flip-flop. Moving on to the D flip-flop. So let's take 5-minute break if you don't have any questions. So let me see if you guys have any question. Okay, so let's take 5-minute break. From this point, 8:20, we'll be back. Okay, 7:21, sorry, 8:21. Let's get back. And if you go to your canvas, you will find there is a pop quiz too. I'm just setting up a poll so that please answer these if you are ready to put in the quiz password. Hey, I have to know here, like, so you hit yes once you are there to type in the password. Is there any reason there is a no, or it is by mistake? Yeah, I'll share with another poll with the password. Don't worry. I'm just waiting for everyone to be on the same page. 70 out of 78 has responded.
Oh, Professor, the poll disappeared for me, so I can't really respond to it.
But are you ready?
Yeah, I'm ready.
Okay, sure. 73, 70. Is there anyone who is not ready? Please speak up. Yes, Tuong.
Yeah, sorry. Give me 1 second, sorry.
Sure. Tuong, you raised your hand. Any question, Tuong? Yeah, go to your assignment or quizzes section, and that will do.
Professor, I have a question that's unrelated to the quiz.
Okay, sure.
Can you start uploading the lecture videos to YouTube again?
Yeah, as soon as I find some time. I was uploading it diligently because of some of the student didn't have a registered, especially the Open University student. Yeah, but after that, yeah, I need to find time to do that. But you can still access from the Canvas, right?
Yeah, it's just I don't know. I just really appreciate having the automated subtitles from YouTube.
Oh, okay.
Yeah, because
yeah, I'll find some time to upload them. It's on my list, but I'm not getting enough time to get into that. Okay, I think most of you have said yes. So I'm actually sending another poll for the password. Okay. Okay, I think most of you are done with the quiz. And let's see. Polling, etc. And then
Professor,
oh yes,
could I ask you a question about the quiz after class?
sure.
Okay, cool. Thanks.
Or you can send me email if you have any doubt on the questions. All right. So we see that our average score is 75% pass mark. That's okay, I think, but we could do better on this part. And pop quiz is supposed to be on the current topic, but it was on the previous topics, and which already you made some quiz one, and which has a good average marks, I see. So make sure, let's keep up our good work. And next time, probably 85. Let's target that.
Professor, I have a
Yes.
question.
Yes.
So for the quiz, there was a question on there about the consensus theorem, but I don't think the question is right. So I think like the second part has like x,
Yeah, that's
y
my
plus
question.
xz, but
Mhm.
it should be xy plus x plus like the knot of xz. Like
Yeah, can you please send me email? I'll take a look.
okay, all right, thank
Send
you.
me email. If you have doubt on any question, just send me email. All right, so where were we? We have only a few minutes. Okay, maybe we can continue on the D flip-flop operation next day. But before that, I just want to share a little bit with you on this this design. You can do. I would encourage to basically yourself try that. Like you see the code. It's practically we are trying to do here is this D flip-flop with some master D latch and slave SR latch instantiation. That's what we are doing here. To instantiation, you can look at the this flow. Like one master and slave is instantiated with a clock inverted or control signal inverted between them. And then we have this test bench where we are basically changing the C value automatically with a time period of 5. So this always block does it, always. So initialize C as 0, and always after 5 nanosecond, we invert the clock or C. So that practically gives you the clock signal like this. Okay, so this now we are moving from control signal to the clock signal concept, where we are changing this clock signal value at the constant interval of time. And then we are toggling or changing the values on the D input side and see when it is following the Q. We'll see in this circuit configuration, only at the falling edge, Q is following the D value. So this is a falling edge triggered flip-flop, where only at the falling edge of the control signal or falling edge of the clock, whatever the D value at that time, Q is following that. And otherwise, it does not follow that value at all. It is retaining the other value. So we'll discuss that maybe next class. But before that, please make sure if you can experiment yourself in the model sim, that would be nice. Question?
If we have questions about lecture 8, can we still bring them up on Monday, or are we just moving on to the next module?
No, you can ask me questions about any module at any point of time.
Cool, thank you.
As long as it is done. If it is a future module, then I will ask you to wait till others catch up with you. But if it is a previous modules, definitely we can always discuss. Okay, well, one more point. I see there are some jokes going on in the chat. I appreciate that to make ourselves little less burden with day-to-day work, but can we keep it a little bit study oriented and professional? Okay, your jokes and all this stuff can go in other websites and other chat rooms. Okay, not in the classroom, please. All right then. So that's all. Good night and good luck for your submission on the project 1 tonight, and start on project 2 immediately. That is very, very hard, 100 times harder than project 1. Okay. Good night and see you all in the next Monday.